Welcome back. We're going to talk about what happens name-wise to carboxylic acids once you deprotonate them and you end up dealing with a conjugate base. All right, so what's going to happen is that because you have deprotonated the carboxylic acid, it's now an anion. And what that also means is that you're going to have a cation to counterbalance the charge of the conjugate base. So the first thing you will do is you will name the cation like you normally do in ionic nomenclature, right? And usually we're going to be dealing with alkaline metals, maybe ammonium. Technically, you could use any metal for this. It could be like a metal that has Roman numerals for the charge, but we're probably going to stick to like the simple ones just to avoid, introducing too many moving parts at once. So after you name the cation, you have to then name the anion. And the way that this works is that you name it as if it were just a regular carboxylic acid, except that at the end, you will get rid of the suffix ic acid and you will replace that with the suffix ate. And this is very much reminiscent of what you guys have done in general chemistry, right? If you remember, acids like nitric acid becomes nitrate once you deprotonate it, or sulfuric acid becomes sulfate. So it's the same logic apply here, right? Except that we're kind of like modifying the carboxylic acid name, which changes from carbon chain to carbon chain. All right, so let me show you how this plays out. So you could have something like this, right? And then the idea is that you gotta realize that you got your carbonyl oxygen double bond, moiety right here, and attached to that you have your oxygen that is singly bonded. Now it is on that oxygen that you have to have a hydrogen for this to be a carboxylic acid. But if instead you have a metal such as sodium, well, then what that's telling you is that you have substituted hydrogen for a metal, and that makes this whole thing anionic. In essence, you're dealing with a conjugate base. So we gotta first name the cation, which is sodium in this case. And one more thing that I should probably tell you before we get into the naming, I have different ways of presenting the same conjugate base ionic salt. Sometimes I'll present it like this, just right next to each other, now. Other times I'll draw a bond between the sodium and the oxygen to emphasize that connection. Or other times I will draw them like they probably ought to be represented anyway as an ionic interaction, right? Because no matter how this is drawn, it is an ionic bond that you're dealing with, right? At the sodium oxygen connectivity, right? So you got to keep that in mind. Don't think of this as covalent. It's not, but the sodium is there to counteract the charge of the deprotonated oxygen, right? So all of these are potential options as far as looking at the example. So as I was saying, you name first the cation, which is sodium, and then you name the anion, right? And you have to do the same thing as we did before. You look for the longest chain that contains the carboxylic acid. So this is 1, 2, 3, and 4. So it looks like butanoic acid. And then you have two methyls at position 2. So this is looking like 2,2-dimethyl butanoic acid. And simply, the ic acid is dropped and replaced with 8. So instead of saying butanoic acid, now you say butanoate, right? So altogether, this is sodium 2,2-dimethyl butanoate. Okay, let me then show you a couple more examples because I'm gonna play a little bit around with the possibility of having multiple carboxylic acids and also multiple cations. So yes, the cations have to be named first. The anion is named as a carboxylate, right? So you replace the ic acid with with 8. And then here you have a few possibilities when multiple carboxylic acid moieties are present in the same molecule. Some of them could still remain protonated. And if that's the case, right, you have something that's deprotonated, but then something that is protonated from the point of view of the carboxylic acid moiety. You will basically spell out that hydrogen by saying hydrogen in the name. And you say that after the cation name, but before the anionic name. If, on the other hand, you do happen to have different cations balancing the charge of different carboxylic acid moieties, then you simply list those cations alphabetically in respect to each other. All right, so let me show you some examples. So we could have the following dicarboxylic acid, or technically dicarboxylate, which is balanced by the single cation with a 2 plus charge, magnesium, in other words, right? That single cation balances out the charges of both of the carboxylic acid conjugate base moieties, the carboxylates. Now, if you think about it, this thing has a common name. This is phthalic acid. But if you deprotonate it fully, then it becomes phthalate. So altogether, this is magnesium phthalate. Okay. And by not including any prefixes in the phthalate name, we're already saying that these two moieties are ortho to each other. Okay. Now, another option could be that you do have one out of the two carboxylic acids deprotonated, right? So only this one up here has a metal instead of hydrogen. But still, the whole thing is now anionic just because of the one carboxylic acid that has been deprotonated. So you still name potassium first, and then this is still phthalate, but because one of the carboxylic acids does have hydrogen, you first say hydrogen, and then you call it phthalate. So potassium hydrogen phthalate. And if the name rings a bell, it's probably not a coincidence, because this is also known as KHP. K for potassium, H for hydrogen, P for phthalate. This is literally the go-to color indicator that we use for acid-base reactions, and that we use very commonly for titrations. So you might remember, starting with a solution, an acidic solution that is colorless, and upon adding base to it, eventually turns pink, right? That pink coloration is a result of having fully gotten rid of all the protons of potassium hydrogen phthalate, and then allowing the indicator to show, that pink coloration that lets you know the titration is over. But the reason why we tend to use this particular acid is because technically, as a result of the high molecular weight that it has, at room temperature is a solid, right? And here's an actual crystal of KHP. So it's very easy to measure, very easy to use. So it's kind of like one of the go-to acids to do acid-base chemistry with, right? Okay, and then one last example. Here we have different cations. So we have NH4 plus, and then we have K for the two carboxylates. So here you have to go alphabetically. NH4 is known as ammonium, and K is potassium, right? So A goes before P, so they should be known as ammonium, potassium, and then phthalate. And then all of the other carboxylic acids that we talked about in the previous video with their common names are, potential possibilities, right? So you could have oxalate from oxalic acid, or you could have malonate from malonic acid, etc., etc. So just be ready for that type of thing. Okay, so with that said, we are done going through the nomenclature of carboxylic acids and carboxylates for that matter. So in the next video, we will talk about anhydrides and how we name those type of molecules as well. Okay, so see you in the next video.